So what happens is, from the bottom and the top source here, they're both going to have the same path difference. So they're going to have constructive interference at the wall. And then you'll have destructive interference where the bottom wave has to travel 1/2 wavelength more than the top one, and they're going to be 180 degrees out of phase and have destructive interference. So if we have a double slit, but we have a bigger, but it's much, much bigger than a wavelength, right? So if we have two slits and it's much bigger than the wavelength, you're not going to have any diffraction. And that's actually what you would see here. This is a data table of this. If we look at the central position, if let's draw this out. So let's say we've got a double slit here. Let's say we have a wall over here. The light is coming through. And when it comes through, if these slits are really big, the light is just going to kind of still just go straight through. It's not going to diffract very much. And the intensity of light is not going to be very different here. However, and this goes back to that definition, right? It takes place when a wave with a wavelength comparable to or larger than the size of the aperture moves through or past the aperture obstacle, and we have that. Now in this case, you can tell, from the graph that, the width is not negligible. If you have an opening here like this, and the light is coming through and you have a bright spot here and then darkness and then bright and then dark, you can actually see that bright and dark here, and the diffraction, is more significant. And then as you get further and further away from the edge, the intensity of the light drops off. So the central fringe is here, and then the intensity gets weaker and weaker as you get further and further from the center there. And that shows that there's significant diffraction taking place. The 0.5 spot here is showing the first fringe that would be n equals 1 there. And then the fringe here. And so they're not as bright, right? They're not as intense. Therefore, diffraction is having a significant effect, and the width of these is comparable to the wavelength. So what is the wavelength of light if the slits have a separation of 4.2 times 10 to the negative 4th meters, and the screen is 3.8 meters from the slits? So I'm going to have you try that. Go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay. So D is how far the slits are away from the surface. Lowercase d is the distance between the slits, 4.2 times 10 to the negative 4th meters. And S, how far apart those are, is 0.005 meters. And we have our equation there. And we can find our wavelength, 5.53 times 10 to the negative 7th meters is the wavelength. So what would happen with narrower slits? The slits are closer together. Well, if we think about that, if this is closer together, this is going to be a smaller number. And if it's smaller, that means that S over here is going to be bigger. So the smaller the distance between the slits, the greater the diffraction that we're going to have, and the more spread out it's going to be. So how far apart is S if the slits in the last problem are 1/2 of D? So go ahead and calculate that out. And so pause the clip and do that. And then when you're ready to check, you can hit play to continue. Okay. So, half of D would be 2.1 times 10 to the negative 4th. And we've got that. So our S distance between them would be 0.01 or 1 centimeters, which would be twice the distance. And so that's a direct relationship there. If the slits are half, therefore the distance would be twice as much. And that should make sense because everything else, the wavelength itself isn't changing, right? And so the other things, and D is not changing, so therefore they're inversely related to each other. So that was for green light. How about for red light? What happens if we have a different wavelength of light? So you can try that one as well. So go ahead and pause the clip and try this one, and then when you're ready, you can hit play to continue. Okay, so yeah, so if you have red light, or red light, 700 nanometer light, and that's in the numerator here, S is going to be greater, right? Because, if you think about the numerator here, with the bigger this number is, the greater S will be. So in other words, the distance from the center here to, here is going to be greater, S is going to be greater than blue light or green light would be shining through. So that's an important thing to see here with that, and that's good. All right, so we've looked at how electric and magnetic waves are, in an electromagnetic wave, are perpendicular to each other. They're transverse waves as they go across. And that's going to be important as we move into our next section here. The polarization of light is a really interesting phenomena, and we've kind of been building to be able to look at it now. Some of the things that we've looked at in this unit, allow us to look at this here. So an electromagnetic wave is said to be plane polarized if the electric field oscillates in the same plane. So in other words, if we had a plane, if our plane in question was up in the positive y and the negative y, in this case here, the electric field is going in the positive and negative y, and so we would say that this is plane polarized because the electric field is going up and down, just like the plane itself here. Here's another visual to see that. In A, it's vertically polarized, and so plane polarized, you can see in the positive y-axis, the electric field matches up. And then in part B, or in picture B, you can see that the electromagnetic wave is rotated, and it's horizontally polarized. And so the positive and negative z-axis, you can see that the electric field matches up with that there. So unpolarized light has light that has electric field orientations in all directions, and most of the light around us is unpolarized. You have electric fields and the magnetic fields rotated in all sorts of which directions. And so if you have unpolarized light and it passes through a polarizer, what happens is it becomes plane polarized. It eliminates some of that light, and then only what remains along with that plane survives. And so if you look at this picture here with unpolarized light, it passes through a vertical polarizer, and then it becomes plane polarized in the vertical direction. So that represents the electric field there. So it cuts out the rest of those that aren't aligned with the vertical. Now, some of these that are kind of in between, kind of like this one right here, this is kind of in an angle. A portion of that will survive, will make it through. Only the vertical portion, though. So light is polarized when electric fields oscillate in a single plane rather than any direction particular to the direction of propagation. So here's your unpolarized light. You've got your vertical polarizer, and it's going to cut out every part that's not vertical. And so, for instance, light that's like this, you're only going to get the vertical component of that passes through. And then what will happen is all your light will then look like this. It'll all be plane polarized in the vertical direction and continue like that. There's many different kinds of polarizers, and there's usually questions about how does this actually work. There's different ways that you can polarize light. There's wire grid polarizers where the electromagnetic waves interfere with the wire's electrons. Only parallel components make it through. There's absorptive ones where there's special crystals that actually absorb the light and let only light that passes through in a certain plane. There's other types too, reflective polarizers, beam splitting polarizers, even using thin films can do it too. So polarized light will not be transmitted. Let's say you've got vertically set polarized light. It's going to make it through. So in this first picture, you can see that you've got vertically polarized light. If it passes through a vertical polarizer, nothing else is going to happen. But if you have horizontal polarized light and that reaches a vertical polarizer, none of that electric field is going to make it. So let's take a look at this visual. This may help here. So let's say you have unpolarized light here. It passes through the vertical polarizer, and now it's plane polarized in the vertical direction. Well, when it hits a horizontal polarizer, and that horizontal polarizer only is going to let through horizontal light, yeah, so it's not going to let any light through. And that's because it was coming in vertically polarized, and then, it's only going to let what's horizontal go through the next part.